Okay, good morning, good morning. I'm going to try this again, and it's not giving me that. Okay, anyways, I was looking to see if my mouse is working, but it kind of is, but it kind of ain't. All right, so today we're going to derive acceleration without any numbers, and we're going to follow the force toolkit. And so the first thing we're going to do is we're going to choose our system. And when we do these two body systems connected by a string, consider this to be like a choo-choo train, right? It's a train, it's got multiple cars, and we're going to consider the whole train moving together at once. So the system is A and B together. Our x-axis is going to be our axis of motion, which is going to be right along the string, up and over the pulley and down. So up and down is both positive because it's along the line that we're moving to the right. They're moving together in unison. If they move the opposite direction, that'll be negative. If they move this direction, that'll be positive. Our free body diagrams, I'm just going to draw it real quickly on the, and my mouse disappears. I'm going to draw it real quickly on here. This is what's making it go. That's my force of gravity. It's connected by a string right here, so that's my force of tension. This tension is pulling it up the hill. Since it has gravity down this way, that will act against it. And since it also has friction down this way, that will also act against it. And it also have a normal force. And so these will be our main forces that are on this object. As we look down, though, the force of gravity in the y direction and the force of gravity in the x direction are also considered because they impact our rate as we go up. And so what I'm going to do now is the fourth step in the force toolkit is to write the Newton's second law equation. The sum of the forces equals mass times acceleration. But instead of just jumping to that, I'm going to define each one of these things first. And so let's start off with just the basics. And so the gravity here, FGB, I'm going to rewrite or redefine as the mass of the block B times gravity. So this will be mg or mbg. This will be FTB, and FTB is going to be the same as FTA because they're a string, and anywhere along the string you'll have the same tension. This FGA is going to be mass of A times G, so this is MAG. And then once again, the force of tension here is going to be the same as the force of tension there. Just making some definitions here. Okay, and as we move down, then we have our pictures here. This force of gravity in the y direction is the force of gravity directly into the hill. This gravity here in the regular normal straight down direction has two components to it. It has a force of gravity that is going to cause the normal force, and that is my FGY. And then it has a force of gravity that is actually pulling it down the hill. So part of it is pulling it down the hill, and part of it is going into the hill. And FGX is the part that is pulling it down the hill. So mathematically speaking, FGY is the cosine of theta. It's adjacent. The cosine of theta times the hypotenuse, which is MAG, which is FGA. And then this one, FGX, is the opposite. So it's sine theta times mg of A. And so those mathematically will give me what I want for that. Okay, continuing on. Then I have the normal force. The normal force is going to be the opposite of FGY. And so this normal force is the opposite of FGY. They are the same value, same size vector. They cancel each other out. The friction, Fk, is going to be mu sub k times Fn. It always is that way. But since F of n is Fgy, and since Fgy is mag cosine theta, then the friction will actually be mu sub k times the mass of block A times gravity times cosine theta, and that will give us our friction. This is important for our next step. Our next step is we're going to look at the Newton's second law equations. And the second law equations in the y-axis, really there is only one thing in the y-axis. It's just this. That's in the y-axis. Well, this looks like it might be in the y-axis too. It's not. Remember, this is in the x-axis because it's along that line of action. So this is the only thing we have in the y-axis. There's nothing going sideways here. That would be weird. It would be a different axis altogether. But so in the y-axis, they add up to 0, right? Because Fn and Fgy cancel, as we said before. It's not going to jump up. It's not going to go into the hill. They're going to cancel each other out. However, in the x-axis, we're going to add up all the forces to the right minus all the forces to the left. So let's consider what we have. We have a force to the right, which is down, which is pulling us over the pulley down the hill or over the edge of the hill, and that's FGB. And then with the force of tension pulling back, the force of tension pulling forward, the force of kinetic friction going backwards as we drag up the hill, and the force of gravity in the x direction pointed down the hill. And so we're going to make a statement with those items. The forces, the sum of the forces, is always equal to ma. That's the Newton's second law statement. From there, we have the force of gravity down the hill. We have these two items. These two items are the tension, and the tension are going to cancel each other out. This is going to be the same as that, positive and negative. So what's a million minus a million? What's 100 minus 100? It will cancel out. This will be 0. This will be the friction against us, and this will be the gravitational force in the x direction against us. And that is always equal to ma. The mass is the two blocks together, and that's our A. So our statement here is going to be rewritten like this. FGB is actually mbg, the mass of B times gravity. Fk is actually mu sub k times the normal force. And then FGX is just the x component of gravity down the hill. So this is pulling us right, and these two things are dragging us back down the opposite direction left, and that's why they are negative signs. Positive, minus, minus, these two are to the left, this is to the right. Here's our two masses times acceleration. We rearrange this, and we've solved for A. And there we go. Your acceleration will be the mass of times the gravity of the object pulling us to the right. The deceleration, or the negative acceleration, will be the friction pulling against us, and the force of gravity pulling against us as well, divided by the two masses together. Finally, we can rearrange that for acceleration and actually distribute out the g. And so the g distributes out, and we get this final idea. And I will come back and finish this later.